a bank can decline a payment if we had the money, the sufficient amount of money in our bank account, and we're like, hey, I want to pay Joe blah 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 this amount of money because he did this service for me. The bank, for some reason, whatever reason they may have, they can say no. You are not allowed to send money to Joe, right? And so one, it's like, who are you to tell me how to spend my money? Because to me, that idea really blew my mind when it's like, I earned that money, put it in that account. Then you're going to have the nerve to tell me that I can't pay someone for something that they've done for me. The purpose of Bitcoin, it is a purely peer-to-peer version of electronic cash that would allow online payments to be sent directly from one party to another without going through a financial institution. Welcome to the Adapt or Die podcast. This podcast explores ideas related to self-growth, finding meaning, and living a more fulfilled lifestyle. It's your host, with the most, Armel Tala.
And it's your host, on the low, Ben Smith. We're two college students on our own path of lifelong learning with the hope that you will join us in our journey. And now, it's time for the next episode of
the Adapt or Die podcast. Welcome back to the second, and if you guys don't know, but the actual fourth recording of this blockchain series. Unfortunately, audio got messed up, so I am really hoping that nothing goes wrong on this part. We double checked it this time, so everything should go well. But hey, I'm not upset if I have to talk more about Bitcoin.
I know he was like,
blockchain.
We can just do one episode. I was like, we'll record both episodes.
I know when you texted me, because Ben was texting me, like, yo, this audio is messed up, bro. And then I was like, let me check. And I was like, dang, like we messed it up. Like I wasn't happy that it messed up, obviously. But then I was like, I felt bad for Ben because I was like, yeah, no, we spent a lot of time doing it. And I was like, we could probably just put it together in one, or maybe just cut out an episode. And then I know he texted me like, nah, we can do both. I know he said that for me. My heart got a little warm. Heart got a little warm, but so that means we actually finished Thanksgiving. We went through Thanksgiving. How was your Thanksgiving?
It was pretty good. I had way too much pecan pie, bro. So good, dude.
People be eating pie in Thanksgiving.
You don't eat pie?
No, I don't eat pie.
How was your Thanksgiving?
Clearly
it was pecan pie-less, but keep going.
It was pecan pie-less. There was some apple pie. My aunt was like, "You gotta eat my pie. I bought it." I was like, No one asked for pie. Like we're African. Like we're like, and my mom was like, "We're just gonna do like a the typical American Thanksgiving." And I was like, "Yeah, this is kind of average, bro. That was alright.
Mid.
It was kind of mid.
I got
you. We need to throw in some little African spice in there, but I had a good Thanksgiving. It's much easier to talk to parents when you're older.
That's true.
Like, I don't know. Maybe they just stop seeing you as a kid. Maybe you can actually start saying words.
They talk to you like a real person.
For real.
Those ideas and stuff.
For real. Like, bro, it's insane. And of course, I was talking about crypto and blockchain again.
I was talking to my grandparents and my parents we had a whole conversation about crypto.
Really?
Yeah. My grandfather, because I've been like talking to him about it. And so he's getting more into understanding it, I guess. Mm-hmm. Not like crazy, but he talks to anyways. Yeah.
That's interesting. I'm going to have to hear more about this offline, but.
Offline.
I wanted
That's
to use
from
that so bad. But all right, enough with the talking. This is the second episode of the series of the blockchain series, based on our book, The Basics of Bitcoins and Blockchain by Antony Lewis.
Antony.
I don't care. Antony Lewis. Great book. I was saying great author. And
good book, yeah.
Today will be a bit technical, and we're going to be diving into more about understanding how digital money works first off, because everyone uses money, but no one even knows how it works before. Yeah. Honestly, I didn't even know like 94% of money is digital, like the money in circulation. Like I don't know, that thought never crossed my mind. Like
we're already like a digital economy. We've been that way for at least a little bit, for sure,
for a while. So we're going to talk about that, and then we're going to talk about the basics and really understanding how we came to build blockchain and the first Bitcoin. So, but Ben, if you can start us off.
For sure. The first thing we need to understand is just a little bit of basics about the bank system and how transactions operate currently. So, the first thing is when you make a transaction, let's just say you're at Walmart or something, right? If you're paying in cash, that cash is actually important in that it gives trust to the supplier. Okay, so like when you go buy some $20 shoes at Walmart. When you give Walmart that cash, they're like, okay, this cash can clearly be used as legal tender in the U.S. And because of this, I trust that it can be used, and I'll give you the shoes, right? A different problem arises once you start having digital money. And so the first thing to understand is that digital assets or digital anything can be copied very easily. So when you're at Walmart and you have your credit card and you're trying to pay money for those same shoes, how does Walmart verify that there's actually money that you have that will be transferred into Walmart's bank account that they can use? And so um, what happens is, for the most part, or what happens is we actually use third parties. We call them banks. And so these banks, they do a really important function of bookkeeping. So they keep track of all of our assets, all of our money, and make sure that no one is double dipping with their assets. So that no one's double dipping with their digital currency or whatever, right? And that's really important because if you could spend $10 twice, then the $10 wouldn't be worth $10. It'd be worth something else. And so that's a
Yeah.
really big issue. So the key point here is that banks operate as a central bookkeeper for all of our transactions. And so what does it actually look like in the banking
And how
system?
does that work? Like how do banks, because I know this whole idea of banks actually sending money to each other. It's not
Hmm.
like money actually leaves one bank to another. It's like the bank doesn't go, oh, I'm Armel. Like Armel just spent $10 at Walmart. Let's
Right,
take this $10 bill that we have in the bank reserve and let's go give it to Walmart's bank. Like how does that actually work?
right. So what really happens is, let's start with the first scenario, which is that me and Walmart hold the same bank. We probably don't, but just go with it for now. We'll say it's Capital One. Okay. So if I'm paying Walmart, what would happen is Capital One has a bank account for Walmart and a bank account for us or for me. And so when I'm trying to pay $10 for those shoes, what they do is they just decrease the amount of money in my account by $10 and increase the same amount of money in Walmart's account. So Walmart's account will go up by $10 and mine goes down by $10. And then that net, it's even with for the bank. I lose $10, which would be my payment. Walmart gains $10, and then I get my shoes, and
But
that's how
there's
that
but
transaction
there's still
works.
the same amount of money in the
Right.
bank.
Yeah. Do you have any clarifications so far?
No, that
No.
made perfect sense. That's the more straightforward.
Right. Yeah. So now it gets more complicated. Where um, let's say we have different banks. So let's say that Walmart uses Chase, and I'm still using Capital One. So for the money to get from Capital One to Chase, if this is basically how it works. A lot of times banks will hold accounts with other banks. So in this instance, Capital One would hold a bank account with Chase, the same way that I hold a bank account with Capital One. They hold a bank account with Chase as if they were just a person, if that makes sense. Um, and so what would happen is Capital One would decrease my account by $10 and then increase their account at Chase by $10. And then Chase would decrease Capital One's bank account with Chase by $10 and then increase Walmart's account with Chase by $10. Does that make sense?
It makes sense to me because I've read it and understood it,
Do you
and we
want to?
will add
Yeah.
visuals to it. I guess if I was to add anything to it,
Hmm.
honestly, I'll just be reiterating what you're saying because
You
you
can say it
explained it
again.
well. You explained it well. The only thing I'll think about is literally to just reiterate what Ben says. Try to do in less words is there's the bank actually holds an account with my bank,
Hmm.
right? And then it's just like the same thing that happens as if we both have the same bank account, except that now that it's a bank instead of a person, or
Yeah.
however, right? So it's we'll add visuals. That's
We'll
really
add
all I
visuals
wanted
for
to add.
sure.
That's
Yeah. I
really all
mean,
I wanted to say. I don't know why I threw myself in this explanation. It's
I got
beyond
you.
me. But
Um,
isn't this like really inefficient?
Yeah, so then you kind of run into the problems. I know it seems like there's only like three banks in the world, but trust me, there's a lot of banks. And so for every bank to hold an account with every other bank is a hassle. Actually, a hassle is an understatement to say that it's a hassle. So what really happens is here in the U.S. we have what's called a central bank. You might have heard of it. We use the Federal Reserve or the Fed for short.
Hmm.
Um, but there's actually more than one central bank. They're regional, but that's not the point. The point is how the central bank operates as a middleman between all banks, basically. And so in this same scenario, for instance, like I have Capital One, Walmart has Chase still, so same general stuff. But let's say that Capital One doesn't have a bank account with Chase, and they still need to get the money to Chase so Walmart can get their money, right? what happens is Capital One will take $10 and the decreased $10 in my account, and they actually hold an account with the central bank similar to how they held an account with Chase earlier. So central bank is just another bank. Don't think about it any differently. It's
Yeah.
essentially the same thing. And so Capital One will increase their account with the central bank by $10. Okay. Now Chase will also hold an account with the central bank, and the central bank will transfer that $10 to Chase's account with the central bank. So just to reiterate, the central bank received $10 from Capital One, and then they decrease the $10 in Capital One's account, and then increase $10 in Chase's account.
Yeah.
Chase then takes that money that was increased in their account and then puts it into Walmart's account with Chase. Okay. So all I have to say is that it's kind of just a long middleman where the central bank acts as a middleman between the banks to transfer the money just to get from me to Walmart, and then I get my shoes.
And why do you guys think it takes so long for payments to just get settled? It's like, wow, like, because all of this, everything when a payment actually occurs, we're not going to go into this though. It doesn't immediately actually happen. Like when you swipe your card and everything, it's like it shows a decrease in your account, but what's actually happening between the banks, like you just explained, takes a long time. But that's a whole different story. And the only thing I'll add on that is the way to think about the central bank is just the banks for the banks.
Exactly. It's just like where banks go to bank.
Me and you can't open an account at the central bank. But good old Capital One, Chase, Charles, all that open banks there.
Yeah. So do you have any comments on that or clarifications?
No.
Okay.
I'm just interested in the more interesting part.
I understand.
So now we are going to talk about the foundations, the bedrock of what actually makes crypto.
Yeah.
And that is cryptography.
Exactly. So what I'm going to explain is digital signatures.
But first, actually, could you, before we go ahead, for no one that's ever heard of what cryptography is, could you quickly explain that?
Cryptography is just a branch of mathematics dealing with, I would say, encoding and decoding text is how I think about it, but I'm sure it has much broader applications. So if I'm wrong in the sense of like my scope, forgive me. I'm not a cryptographer in any way. So, but that's generally what it is.
Yeah.
Think about encoding and decoding text and encrypting things. So we'll get a few terms down real quick, and then we'll go over digital signatures, and then Mel will explain hash functions.
Okay.
So encryption is what we call when returning plain text into ciphertext, and ciphertext just being text that is encoded or it can't be read easily, right? And then decryption is turning that ciphertext back into plain text. So pretty basic terms. You probably heard about this in middle school or something like that. Going from there, we have two different types of ciphers, and a cipher is just, I would say is it the key? Actually,
the cipher. The cipher it's just
I guess it's just how
it's a way of doing it. There's different.
Your cipher is just how you encrypt and decrypt the text. But we have two different types of ciphers, and we're going to be talking about one in particular. But there's a symmetric cipher and an asymmetric cipher. So a symmetric cipher is when you use the same key to encrypt the text as you do to decrypt the text. Okay. An asymmetric cipher is where you have two different keys. You have a private key and a public key. And depending on your use case, you use the two different keys. One will be used to encrypt the text, and then another will be used to decrypt the text.
So how does this tie into crypto and blockchain and cryptocurrency specifically?
So we use an asymmetric cipher, a specific type of asymmetric cipher called a digital signature. And this is what validates or helps to validate who you are and who is transferring money. It's the same as like an e-signature, but it's much more secure, I guess. And so let's see, the way a digital signature works. So like we said, we have a private key and we have a public key, right? And we're going to put visuals on the screen just to help you all out. If you're listening on Spotify, just try your best to follow along.
Or go check out the YouTube. Yeah. Go hey guys, real quick, comment, share, please. I forgot to say it in the beginning. I'm going to have to start putting it at the front, but it helps a lot. We really appreciate it. But enough with the shameless plug. Keep going, Ben.
For sure. So we have a private key and we have a public key. And so real quick, the private key is what we're going to be using to encode our message. In this case, our message is going to be some document or something that we sign. And so the private key is going to encode that into some ciphertext. Okay. The public key will then take what's encoded, and it will decrypt it and turn it, basically validate that our digital signature is valid. Okay, and so we're going to go through this process real quick. I think it can be helpful to use like a black box analogy last time,
Yeah.
didn't we?
Mm-hmm.
And so basically what happens is similar, think of like a contract that you're trying to sign, right? If you have to sign that in person, you choose your signature. But if you're using an e-signature, in this case, a digital signature, what we do is we take the text that we're trying to sign, and we take that text and we combine it with our private key, and that helps us produce. I forget, it's gonna be helpful to understand hash functions, isn't it? Or should we just keep going?
You just keep going.
Keep going. Okay.
This thing, you can just use the word hash functions, and then we'll explain what hash functions is coming up.
Right. And so the private key your private key is going to use the text that you're trying to sign along with your private key, and then it hashes that, or it uses a hash function. You can think about like your private key and the text going into a black box, and then out comes just a bunch of random characters and letters and stuff like that. That is our encryption text, right? And then from there, anyone can use your public key and then the encrypted text that came out of the black box to verify that you did or did not sign said document. That's basically how digital signatures work. I hope you followed that along. We're going to have, again, visuals to make this easier, but yeah.
Yeah, very complicated topic, but as Ben was talking about, there's this thing called hash functions, right? So you have your private key, and then you have that message, and you're putting it into what it's called like a hash function, right? And this is the box. And really, without the hash function, like your private key it's kind of useless.
Doesn't
But
matter.
the hash function, what it does, it takes those two informations and outputs what they call a message, or a just simply put a hash, which is just a, like, practically, you think about it, those private key and the message re-scrambled in different ways to create a different message that is hard for someone to tie it back to the original private key and everything. But so exactly, what is a hash function? And a hash function, again, this is cryptography and it's math based. It's a series of mathematical steps in order to receive a hash or message. So simply a string of characters, most often letters and numbers, right? And so that's what the hash or the message is. It's very long, and it's not really human readable. It's not a sentence or anything like that. It's just a bunch of random characters and letters and numbers. Simple way to think about this is when they say mathematical steps, it's not some crazy, it doesn't always have to be some crazy math that's happening. Like, what is actually used for the crypto and blockchain, for the blockchain and Bitcoin protocol, is a complicated math function. But a hash function can be as simple as, okay, I want to take the first letter of any message. So if I was to say this is the hash function, we'll call this hash function 1. Hash function 1 is take the first letter in any message. So, hi Ben, I will take the H, right? So then the hash will be just the H, right? And that is our mathematical step. It seriously can be that simple. Yeah. Or there's different hash functions where you can take the, like, okay, you know how A is 1, like, and correlated A is 1, 2, B is whatever, blah. You can add the sum of those up as well. Like, there's different ways you can create these mathematical steps. It's very arbitrary how you decide to do it. So going with hash function 1 or hash 1, very simple. Take the first letter in a word. You can think of that, and then our output is hash. But that isn't a great hash function, right? And so there's these things called cryptographic hash functions, and they have 5 main properties, and this is what is used in cryptocurrencies. Number 1, the first property is the same message always results in the same hash. So hi Ben is always going to come out to being H. Number 2, it can quickly compute any given message. Very simply, we take out that one. And for a bunch of different ones, like let's say we use the example of adding the sum of each letter's placement, I guess, in order. I don't know how to actually perfectly say it. I would say like their lexicographical number or whatever.
You can think about it like every character has a number tied to it, and you just tie the corresponding number to each character together to get one number.
And then you can sum that, right? And so no matter which way, you want it to be very quick to compute. And so using hash function 1, H, just take the first letter. Number 3, the third property is you cannot return to the original state. So just by you knowing H, you don't know what the message it could be. It could be how finny. Who knows? Property number 4. The new hash value should not resemble the old one with a small change. And now this is where my hash 1, where my very simple hash function fails. Because if I was to say change it to hi Draylon, like it would still be H. And therefore, this is not a cryptographic hash function. And so this is where you start to introduce more complex hash functions, like what's actually used in the Bitcoin protocol is SHA-256. We won't go into what that actually is, but you can look up. There's great videos. 3 Blue, 1 Brown. We'll put a link down to his video below. But that's number 4. And the 5th one is it is hard to create the same hash value out of 2 different messages.
Right.
So you have 2 different messages, should not really be the same. So just to repeat, the hash functions that are used in crypto is called a cryptographic hash function, and it has 5 main properties. Number 1, the same message always results in the same hash. 2, it can quickly compute any given message. 3, you cannot return to the original state. 4, the new hash value should not resemble the old one with a small change. 5, it is hard to create the same hash value out of 2 different messages. And that is the really heavy, beefy part of that's really what makes crypto. When people say like it is cryptographic, encrypted, like the Bitcoin, the protocol is encrypted, like nothing about the actual protocol is like the information on the blocks. Like you can go and read every single transaction that happened. You will know what address like one person sent to another, like where the money's moving from, how much money is being moved. Like that is all transparent. That is the aspect of Bitcoin that people talk about, like, oh, there's transparency. But the whole actual encryption is when it comes to me and you sending, because that's the most important part. If me and you cannot send the money and know that like, oh, I know Ben is the only one that sent it, or I know like, this is the actual person I'm sending it to, then that's where it all breaks. So this is the meat and bones of it.
Exactly. I do want to make one clarification, just addition real quick, because it'll come in handy later. But this is good to know. A hash value, so when we're talking about cryptographic hash functions, I think just generally in hash functions, they're one way. So what that means is that there is no feasible way for you to find an algorithm, or not going to just a pattern, some rule, some math, such that you could take any answer from a cryptographic hash function and return to its original state. He said that before, but I just want to reiterate because that's like key. And the only way you can figure out what the hash function is to basically just test it.
Try every single possible combination.
You just create your own hash function basically, and then you just throw in different stuff, or if you know what the hash function is, then you just throw in different inputs until you get the correct output. And as we will see, that'll come in handy later. We'll reiterate when it is important, but just know that that's a pretty important fact.
Like SHA-256, that has I think it's 2 to the power of 256, which is an absurdly large amount of trials. You would have to, there's a lot of possibilities of what the answer could be. But now to actually building the foundations, like how do you take a centralized system and turn it into a decentralized network?
And the first question is, what is Bitcoin's value proposition, or the purpose of Bitcoin, centrally speaking?
So to quote straight from Satoshi Nakamoto's white paper, a purely peer-to-peer version of electronic cash would allow online payments to be sent directly from one party to another without going through a financial institution. Let me repeat, because this is huge. The purpose of Bitcoin, it is a purely peer-to-peer version of electronic cash that would allow online payments to be sent directly from one party to another without going through a financial institution. So how we talked about at the beginning, that the way digital money actually works now is that it goes through all these different banking systems, so one bank has to talk to another bank, and then there's a central bank involved when it's interbanking payments. But with Bitcoin, it's trying to say we don't need all those middlemen. We can just send this money through the internet directly to one another without having to go through an institution.
And why so we have like these banks as bookkeepers as our central middlemen, but why is getting rid of these middlemen so significant? I know it's like that seems to you maybe kind of obvious because you've been in the field for a while, but like why? Like that's a central question that I had when I came in. I was like, why is that?
Number one is, I think the biggest for a lot of people that join the space, it creates a more censorship resistant money, right? So with payments that we do like normally with our credit cards, with our debit cards, a bank can decline a payment if we had the money, the sufficient amount of money in our bank account, and we're like, hey, I want to pay Joe blah 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 this amount of money because he did this service for me. The bank, for some reason, whatever reason they may have, they can say no. You are not allowed to
Mm,
send money to Joe, right? And so one, it's like, who are you to tell me how to spend my money? Because to me, that idea really blew my
right.
mind. When it's like, I earned that money, put it in that account, then you're gonna have the nerve to tell me that I can't pay someone for something that they've done for me. Like, it's crazy. That idea to me is crazy. And then two, just the fact it's decentralization. So we don't like, banks have done a lot of sketchy stuff, you know. There's been a lot of, sketchy things that happen.
Shout
We
out
can talk
to
about Wells
housing crisis.
Fargo, housing crisis, a whole bunch of things. So having the power of just handling money, giving it to one central party, one central authority, which they can do a bunch of things like, print more of the money and devalue how much the money is worth in your account. It's something that is a bit terrifying, and it's just like, why would you want to give up that power? Like, that is not their job. That was never their job when it was first created. We resisted creating a central bank because we again know power goes to people's heads and people easily take advantage of it. That's just a simple way to
Yeah, that
put
was
it.
that was a good. That was a solid answer. I even there's some things in there. I was like, wow, yeah, I kind of forgot about that. But now it's time for the real frame of the episode and constructing a or understanding how we create a decentralized network, uh, what we know as Bitcoin. And so the first thing or the first problem that I want to ask you, Mel, is how do we create an account? That's like the first, like with banks, we have, I have an account with the bank. What does it
Yeah.
mean for me to have an account with Bitcoin? Like what, like, I mean,
Yeah.
I know it's not like an account, but like, what is that? How do we start that process?
And so with banks, you need to ask permission, right? And for most people, it'll be like, well, it's pretty simple. I just go online and I just, sign up for that bank, and it doesn't seem that difficult. But that is a form of you asking permission. You have to go on there. They're going to ask for personal information, and and you can get rejected. Certain people, not everyone has access to create a bank. That's a perspective that not everyone kind of realizes. But with crypto, with Bitcoin, it's permissionless. So what we use is how you described earlier, the public keys for you to create an account. And you don't really have an account. What you have is an address that people can send you money to. And you get to create this. No one can stop you from creating it.
Mm-hmm.
It is very simple. And so how you create this address is you use your private key. So your private key is, I think we talked about this earlier. But so your private key, you just pick really any number between, I think it's 0 to 2 to
Two.
the power of like,
Yeah, it's basically you pick a number that has 78 digits.
yeah, between
It's a lot
0
of
and a
digits.
number that has 78 digits, and it's super super long. So you just pick one of those numbers, and then you use that, you put into the SHA-256 hash function, and then you get your public key. Am I
Okay.
wrong on that aspect?
I think yeah, that's right. Yeah, yeah. You just because you choose the private key,
Mm-hmm.
and then
You use the
yeah,
SHA-56 to get your public
and that
key.
creates a public key,
And like we mentioned,
and everyone can see the public key, but
Mhm.
you'll use your private key to do all your digital signatures and
Yeah.
stuff. Not that you're actually doing them yourself, but yeah,
yeah. And
yeah,
so
you explain that right.
again, like we mentioned, that the hash function is asymmetric, so you cannot derive the private key from the public key.
Right.
So anything you want to add? Okay, yeah, but you
Sounds
cannot
good to
derive
me.
your public key from private key, and then there's another layer to actually get your address. Then you take that public key, you then again put it through another mathematical. I don't know if it's the SHA-256 on this aspect, but you derive your address from your public key, and so that's how you get the address where people send you the actual Bitcoin. So there's
Okay.
some steps to it, but
Okay.
essentially you're just using your public key. You're taking this number that you arbitrarily pick yourself from a very wide range, and then you get a public key from using the SHA-256 hash function, and then you use that to then create your address, and then that is where people can send you money, and that is your account.
Mm-hmm.
So, but the difference between this and a bank is that you don't need to talk to anybody to do it. You can just go to a website that says help me pick a random number
Right.
between something to something. Then you can find the SHA-256 function. It's online. Everything is
Hmm.
completely free and available for you to do. That is the difference. It is a permissionless system. And one worry people may have is, what if I have the same address as someone? Well, the likelihood that you do end up picking someone's same address is super, super low, because the numbers for you to pick from for your private key is between 0 to 2 to the power of 256.
If you don't know how big that is, I'll put it this way: no shot, Chief. It ain't gonna happen.
It is not going to happen. So that is the solution to problem number one. Like, how do we allow people
Right.
to create an account without permission?
And so now that we can create quote unquote an account with Bitcoin, which is just your address, how do we actually keep track of who's sending who to who? Because we don't have it's not like Chase is like, oh yeah, Mel sent Ben $5 for dinner. It's just Bitcoin is, it's decentralized, right? But how do we create a decentralized bookkeeping such that we can all agree on who sent who what without a centralized authority directing all of that action?
So the reason why we're saying that we are destructing a centralized system into a decentralized network is that key difference between system and network, right? And so we're creating a network, meaning there's going to be what they call nodes. So these nodes, you're just seen as someone that runs the Bitcoin's code on their, they run the software, the Bitcoin software in the computer. They then can become a bookkeeper. So anybody in the world, if you have a computer, as simple as that, even if you have one of those cool new iPads, you can pull up.
They're very cool.
You can
by
pull
the
up
way.
the Bitcoin software, the code. It's all on the website called GitHub. You can read the code yourself if you want. Run the software and you become a bookkeeper, right? And so when someone runs that software, they become a node in the network. And so let's say you run the software, then I run it, then our friend in New Jersey runs it, then our friend in California runs it.
Everyone can run it.
Anyone can run it, right?
You run it
as
together.
soon as everyone starts running it, these nodes start connecting to each other in a way, because we're using the internet, right?
Okay.
And so the nodes know, like, oh, someone else just started running the software. Oh, send them the book that they're keeping. And so
Do you
to
know
get to your
off the top of your head, like how many? I guess each node is considered a minor. Am I correct in saying that? Or I know mine. That's like a different.
there's a bit of a difference. So
Okay.
like you can be a bookkeeper and not be a miner. You can be a miner, but I think
Okay.
most miners are also
Yeah,
bookkeepers.
we'll
as
get to
well.
mining later. So for now, just for safety, I'll just say bookkeeper.
Yeah.
Do you know how many bookkeepers there are at any given moment, and then like how many? Let's say in a span of 6 months, how many bookkeepers there might be? I know that's kind of a random question.
Yeah, there's about 12, I think 10 to 12,000 like nodes in the network
At any given
right now.
moment.
Yeah.
Oh, okay. That's a lot, because it's like
and it's spread
they're not
across.
on all the time, are they? Because it's like, isn't it?
Yeah, so nodes, so you can stop running the software and hop back on. And the beauty is, so to answer your point of like, how do we keep a decentralized book, is that all these nodes, once you hop on the network, another node that's been on the network will propagate or will send you all the history of all the transactions that have happened. So what we're doing is we're taking so the bank will keep one book. They'll be like, okay, they keep track of all the transactions that happen. But this time what we're doing is taking that and then just copying it and sending it to everybody in the network.
I see. Yeah.
And so, yeah, and to answer your question, you can drop off the network, come back on, and then all the transactions, the book, right, will be propagated through the network, and then you can get it. Then you will get that on your record, and then be able to act as a bookkeeper.
Okay. Yeah.
Anyone can just, and the beauty of it, like anybody can just come on and come off anytime they want. And now having 10 to 12,000 people, not everyone is on all the time, but most of them are on all the time.
I
because
think it's like
miners.
10 or 12,000 are on at any given moment, and then like
there's like a total.
I think the total amount over like the total number of bookkeepers over like 6 months or something is like 1 million or something like that, which is it's a lot. I could be wrong in the scale of that, but I know it's sizably more than 10,000. Like is a good amount.
And the thing too is it's spread across all different countries. There's some in Europe. There's some running in Africa. There's some running Australia. Some in South America. So again, decentralized, and the beauty of it being decentralized is that if the government wanted to say, if the U.S. government said, "Hey, we want to stop it," sure, okay, you can tell everybody in the United States to stop running it, but you still have all these other countries, and that means that it's still usable. Me and you
Right.
could still send Bitcoin even if no one in the United States is running a node on it.
Okay, so we have all these different bookkeepers,
Yeah.
right? But how do we make sure that everyone's on the same page as far as transaction ordering? Like, how do we make sure that like my book of when
hmm
transactions took place is the same as your book and everyone else's book? How does that work?
Yeah. So this is a very interesting solution that Satoshi Nakamoto had. And so the problem with transactions is that it's not that everybody in the network automatically knows when a transaction occurs. So if I send you 1 Bitcoin, the nearest, this is, I'm making a bit of an assumption. I don't know exactly, but I'm pretty sure that the nearest bookkeeper will get that transaction recorded on their book.
Hmm.
Once they get a transaction, they have to send that to the rest of everybody in the network. And remember, we have people in Africa, we have people in different
All over the
countries
world.
all over the world. So it takes time for these transactions to get across. So we can't order them transaction by transaction. So the solution that was proposed by Satoshi Nakamoto was, let's just group these transactions together after a certain amount of time. So
Mm. Okay.
let's let an amount of transactions get propagated through the network so that everybody has a record of it, and then let's batch those up. And so this is where the name block comes in when it comes to blockchain, is that we're grouping these transactions into different blocks. So that means that bookkeepers perform two functions now. So they're validating and propagating pending transactions, and then two, they're validating and storing and propagating block transactions. And we're going to talk more about how the actual creating of blocks works. But so by slowing down, so what blocks do, by grouping them by blocks, it slows down the data entry into the network, right? And so blocks are what actually confirm that a transaction has occurred. Like when you send a 1 Bitcoin, that's a pending transaction. Until it gets grouped together into a block,
I see.
it can't actually be fully confirmed and settled, if that makes sense. So by slowing down this process of data entering, you allow all the different bookkeepers and nodes to to agree on an ordering on those blocks. So
Okay.
it's easier for us to order the blocks than it is to order each transactions, because the thing is, it takes about 10 minutes for each block to be created. So that gives all the nodes more time to say, like, okay, this 10 minutes went by, this is block one, the next block, and the next block.
So the ordering, generally speaking, is not linked at all to when I send the money. It's only linked to when the bookkeepers create the groups of transactions and then
hmm
propagate them. So it's like, even though like, I could send you money and then you could send me money 2 hours later, but your transaction could technically go through before mine if just luck had it, or if you
Yeah.
I think if you use transaction rewards, like fees or something.
hmm
Um,
And we'll get more into the
yeah.
bit details, but yeah, that could happen.
Okay.
And
Because that confused me for a while. I was like, wait, what's the actual order? But the order's created with the blocks, right? With
mhm,
the groups of transactions,
yeah,
not at all with the sending and receiving the money. Or
yeah,
technically, yeah.
yeah, 100%. And the thing is, you could send a transaction. It may take even a couple years if miners did not decide to put that transaction into a block.
So I know you. So the next issue we have, that I have written down at least, is who can create blocks and how often. You kind of touched on both of these, so I'm
hmm
gonna ask you a different question that you may or may not know. Do you know how many transactions are in each block, and a block just being the group of transactions?
It varies. There's not a number that I've seen,
Mm-hmm.
but it is 1 megabyte. So again, this is software. So a block is 1 megabyte of transactions, 1 megabyte of data of those transactions. But
Mm-hmm.
it isn't. I didn't fully explain I explained who can create blocks technically, but
Yeah,
it
yeah.
is a
But
lot more.
how do we certify that everyone's creating? How do we make sure that no one's lying about? Like, how do we make sure that a bookkeeper is not saying like, oh yeah, Mel sent me an extra 10 Bitcoin, but like no one else really knows if that's true or not,
Yeah.
or something like that. How do we make sure that no one's cheating the system in this way? That makes
And
sense.
yeah. And so first off, you want to say, like, anybody can be, again, like a bookkeeper, and then anybody can be a block creator, right?
Hmm.
But you don't have to be both. Those can be mutually exclusive, but again, at the same time, those can be the same thing. You could be both. So how do we know that someone's not like gaming the system, or that a block is not invalidly created? it's this idea. Then you're gonna hear this a lot when you start diving more into crypto. Is these different consensus mechanisms, and all they're saying is how do we agree that we're gonna create this block? And what Bitcoin uses, the original consensus was proof of work. And so what proof of work is all these block creators are practically playing a game of chance. And that game of chance is who is going to be the first one to find the number that's gonna allow them to be the ones to create the block. And this game of chance it's a game that's played in aggregate. It takes about 10 minutes. Like I mentioned, each block takes about 10 minutes to play. And so the prize of winning this game is the ability to create a block.
Could you quickly expand on what you mean by find the number that wins the game?
And so, yeah. And so the actual game, to explain, like you said, is you're looking for what they call like a target number. So it's a hash value that is below. So it's a hash value. So what they're doing is they're calculating, like all mining actually is. Let me take a step back.
Yeah.
All block creating actually is to, like, I guess, find this number, this winning prize, is you're just taking. I want to make sure because there's a lot of parts I'm kind of mixing myself up. But so what you're doing is you're taking a number, you're inputting that into a SHA-56, all the data in the block, right? So there's a bunch of transactions that are happening in that gets bundled up into that block. And so then what's happening is you're taking those transactions, all that data, and then you're putting into the SHA-256 algorithm, and then you're getting a hash value. And so what you want to do is, the goal is you're looking for a specific hash value that is below what they call a target number. And so the rule is again, it has to be below this number, and it changes varying. But so what actually happens is, it's not that you're changing any of the transactions that are happening. So people are like, oh, like, if I'm looking for that value and I don't get it, what happens? People keep redoing it, right? And so, but what's actually changing is that there's just one arbitrary number called the nonce. Am I keeping up?
No, keep going. Yeah.
Yeah. And so it's called the nonce, and that's the only number that's changing. So they're not actually changing any of the data or any of the transactions, but they're changing this number, and they keep just practically incrementing by one and keep putting into the hash function. So they're just like, okay, input 1 into SHA-256, get this hash value. Is that below this target number? No, it's not. Okay, do that again, do that again, do that again. Because remember, the SHA-256 is asymmetric, so they can't figure out. They know the hash value, they know what the target number is, or what they're supposed to get below, but they can't reverse engineer that. They just have to keep changing this nonce. And this is what people mean by, like, mining is this is why they call it mining, because there's no like calculation, there's no like super complicated math. It's literally just trying the same function, trying the same math problem over again until you reach that goal. And so mining is very tedious, and it's super repetitive. And one really important thing about proof of work is that it is a one CPU, one vote, which means
expand on that.
So people would think that, hey, if I wanted to practically be the one to win this game of finding the correct target number, wouldn't I just have more nodes in the network, be more miners, and like I would win, right? Like I would just have more nodes running and trying it at the same time. But the thing is, winning the game is based on computational work. Again, proof of work, meaning that the more nodes you have doesn't actually mean anything. If you have a bunch of different computers running, but they're not powerful, they're not fast, because what's happening is all these different computers are racing to find that number. They're all like literally designed to be super fast at calculating SHA-256 and just changing that input. And so if you have a bunch of different nodes that are not as fast as just one supercomputer, it doesn't matter how many nodes you have. You're always going to lose. So the sum of those nodes, the sum of the computation of those nodes, if it's not greater than the sum of like one node that has a higher computational power, then you're always going to fail. So that's why it's a one CPU, one vote, meaning that you're better off combining all of that computational work that you may have to try to be the fastest at finding it than having all these different computers doing it at the same time.
It's kind of, so I guess, like a good analogy that I just thought of would be like, would it be faster to transport 8 people with 8 bicycles 10 miles or 8 people with 1 motorcycle 10 miles? It's like, I'm not really sure what the answer is, but like, it's kind of based on like how, but you see like the analogy kind of, does that hold?
No, it makes sense, because a bicycle, again, requires the work of those people is not going to be greater than the work of the motorcycle.
Right.
And then doing it all at once. Yeah.
Okay.
It's much faster.
I feel like I had a question for you that I kind of just one clarification I wanted to make because you
Hmm.
said it, but it could have easily been missed in passing. Just that the hash value that's created when you're using so the nonce is part of the block, right?
Yeah.
And so just to reiterate, all of the block is put into the hash function. So it's
Yes.
like that's why it's different every time is because the whole hash function is put in the whole block. All the transactions are put into the hash function, and then for each one, because each transaction group is different, you have to find a different nonce to get a certain hash value.
Yeah. And the
Just
way
yeah, but you said that. I just wanted to make sure it was clear for everyone.
Yeah, and the way to think about that is like all the different data. Transaction one, it's like in to throw it in the box of SHA-256, right? There's
Hmm.
transaction one, transaction two, transaction three, all the way to the last transaction. Then the only thing that changes is the nonce. It gets added in there. So all that's happening is they're just changing that last number that they're putting into the box to
Right.
get the output.
Okay. And now comes so if block creating is pretty monotonous, pretty boring.
Pretty intensive. It's
Yeah, pretty
it's
a
very
lot of
expensive.
using a lot of energy, a lot of electricity bill going up. How do we incentivize block creators? How do we actually get them to do this? Because I mean, I don't want to do that for free.
Yeah, it's like why would you,
I don't
pay these
care.
high
Yeah,
your electricity bill come in, you're like, bro, how am I
I
supposed to pay this?
heck no.
That's just some Bitcoin. But so the solution to incentivizing is transaction fees. So whenever you send a transaction to kind of abstract the details away, you're going to leave a set amount. Like at the beginning, it was said that you decided the fees that you want to put. So there's a transaction fee that is attached to each transaction, and
Okay.
usually at the beginning it was the sender that would decide like, okay, how much am I going to put for the fee? I may have changed to where there is a set amount. I'm pretty sure there probably is, and I think it's for the better. And so that's what it is. So each transaction has a fee. And so when you're creating this block, you have all these different transactions that have fees and it adds up. And those fees are in Bitcoin. And obviously then they can take that themselves and obviously convert it to whatever they want to or
Hmm.
just store the Bitcoin. So that is the incentive is when you're creating these blocks, each transaction has a fee, like I've said again, and that all the fees add up and then obviously that is the reward they get. And the thing is the fees are critical because the idea that you can choose what fee increases the chances that your transaction gets confirmed faster. So at the beginning or whenever they decided that it was optional, so
Hmm.
you would decide when you wanted to put the fee, the the transactions that had fees attached to it were more likely to get added to the block and be confirmed
Of course.
than those because obviously the miner is like, hey, I want to put
Get
the
a fee.
transactions. Yeah, I
Yeah.
want the money. Like I'm not just gonna do this for free. So that is the incentive for block creators.
So I guess a question some people might have or that I had is in the early days, like when in 2010 is when it started, or maybe it
Yeah,
was 09. I don't know,
oh 09.
around that area. Uh, why? Who was incentivized to make? It was to like to be a bookkeeper back in those days because like there wasn't that much traffic. Like
Yeah.
who was incentivized to do bookkeeping back then and why?
Yeah, so there. I mean, with no transactions going through, it's like, how am I supposed to get any
Any money?
fees? And
Yeah.
then you're telling me it's optional as well. So the first transaction in every block that's created is called the Coinbase transaction. And so this transaction is special because it's the only transaction that actually creates Bitcoin. And so this is where Bitcoin actually gets introduced, gets added into circulation. That the at the beginning it was 50 BTC, right? So the block creator would get to write how much Bitcoin they wanted in that
Hmm.
first transaction. Like, hey, I will, create 50 Bitcoin because of this first because I created
Okay.
this block, right? And so that was the incentive at the beginning was even though there weren't any transactions going through, there were no transaction fees, they were able to create Bitcoin and send it to themselves, send it to their own addresses. And so this amount gets cut by half every 4 years. And this is how there's this set in stone number of 21 million Bitcoins. And to repeat the great quote that I heard, there's only three things to be true in life. And this is from Robert Breedlove. That is taxes, death, and 21 million. So
On jaw.
the amount of coins again gets cut by half every 4 years. So I think it was I can't remember exactly. I think it was between '08 or '09 that Bitcoin
Yeah.
was first created. And then so it was 50. 4 years after that, it was 25. After that, 12.5. After that, 6.
Are we at 6.25?
I think we're at
6.25
6.25 currently. But the last Bitcoin, so this halving is going to keep.
Yeah, when do we reach 21 million?
Yeah, this halving is going to keep continuing until 2140. So around February of 2140. Already, most of the Bitcoin is actually in supply. There's already around 19 million. So there's only two more. But the thing is, obviously, as it's halving, it takes more. It becomes harder and harder to create more and more Bitcoin.
Short aside, if you're wondering how, like, you know, if it halves, like, it's never going to be zero, right? Just due to math, if you know, like, sequences in series, I know not everyone does, but there's actually, if you're basically the addition of like halving every transaction, it will reach a finite number, and that finite number is 21 million. It probably isn't that relevant. I just had to mention it because like
it is.
It's confusing.
Like, how can you half and half? Isn't there a point of halving?
Yeah, it's like you're halving, but like if you're halving a number and you're infinitely adding all the numbers, like it's an infinite amount of numbers, right? So how can it ever reach a certain amount? Just know that it does. It works.
There's a math. Yeah, I remember.
You can look it up
in calculus.
Yeah, you can look. It's a calculus idea.
Is it Taylor series? It's some form of series.
Yeah, it's definitely some series. I forget who created. It's kind of, I don't know.
Just know it's more technical than we've already been getting down to.
Yeah, just know that it works. If you want to look up a video on why it works, you can. But just know that it works. It's a math thing.
You don't even need to know that it works.
Yeah,
just understand there's only three things that are that are always true in life: death, taxes, and 21 million Bitcoin. Okay, the government can't make more of it. They can't they can't devalue your Bitcoin. They can't, print more of it. This is the greatness of Bitcoin.
And so, did you feel like you fleshed out that idea pretty well? Okay. The next question I have for you is, as Bitcoin, in these days, Bitcoin has become, a cultural phenomenon. It's becoming a lot more, popular, right? And so more people are going to hop on the network, right, and try to become miners and, get their Bitcoin and make money. How do we make sure that Bitcoin isn't being mined too fast, right? Because the 21 million comes from really just the math of like 10 minutes every transaction over certain years and then et cetera. Yeah. How do we make sure that we're not creating Bitcoin too fast and that creates extra Bitcoin?
And so, and it probably seems confusing when I say 10 minutes to create each block, and that is how a Bitcoin is made. It's like, how is this 10 minutes decided? Mm-hmm. You didn't say that there was a time set on it. So the math is worked out so that it would take around 10 minutes for these computers to race to find the target value that we mentioned earlier before. But the thing is, this target number is actually mathematically calculated from a number they call the difficulty. And so by the name suggests, it is how difficult it is for them to mine. And so as the difficulty increases, the target number becomes smaller, which makes it take more time to compute. I'm over here stumbling on word. Which it takes more time to compute the target number, and how they know to change the target value. I can't remember when it's changed. I think it's every.
I have 2 weeks in my head.
Yeah.
I think it's
every 2 weeks. Every 2 weeks. So what happens is the protocol will look at like, okay, how long has it taken for each block to be created in these 2 weeks time span? Mm-hmm. It'll figure that number out and be like, okay, well, is that around our goal of 10 minutes? If it's not, then it will increase the difficulty and say, all right, we need to increase the difficulty for to figure out for these computers to try to figure out the target value. Or if it's taking a lot longer than 10 minutes, then be like, okay, we need to decrease and make it easier for miners to find the target number and create a block. And an example way to think about this is like rolling 2 dices. So let's say you have.
I'm sorry to correct you. There, die. Anyways,
2 die. My bad. 2 die. But as I'm very dices die. I'm the worst at English.
English is weird, bro.
Really weird.
It's weird.
So 2 die, and so the way I think about it is I talked earlier that there's a target number, but you want to find something below that, right? Mm-hmm. Like that's the goal. It's either you find that target number or you find it below.
Right.
And so imagine you're rolling 2 die, and I say, "All right, Ben, I need you to roll a number below 8." Right. That's relatively
reasonable.
Yeah. Relatively, you have different combinations: 2, 6, 4, 4. Maybe just get
1-1.
Yeah, 1-1. All over here confusing me. But that's a lot easier than if I said I need you to roll below a 2.
That's not possible, but
then your options become a lot more limited.
Limited options.
Yeah, so you literally just have 1 and 1, right? And if anything more than that, it becomes so difficult. So that's kind of how the difficulty works, is that they literally just say they lower the target number to make it more difficult, and they increase the target number to make it easier for miners to get there.
Exactly.
So that's how they prevent this whole situation of, okay, that the supply will actually end up coming faster than we think.
Quick aside, I see your computer's about to run out of battery.
Yeah.
I actually have this charger right here.
Oh, we're good.
Oh, you're good?
Yeah,
okay. I just want to make sure,
We'll
because
make it.
we lost the audio once, guys, and we're already almost an hour into this episode, and I'll be very disappointed if I have to record this again.
Hey, bro, your sides are taken away from the battery time, though.
You're right. Let's keep going. So another problem that we have is, okay, so we have these blocks, right?
Yeah.
Let's say you're working on block number, I'll just say 1001. What stops me from working on, taking a group of transactions and creating a block that will be attached to the block after your block? So I'll be ready. Like, I already won the game, like, before you even started. Like, what stops me from doing that?
So blocks are actually, they're not linked by numbers. So it's not like block 1, then block 2, then block 3. That's not how it works. Because technically, a miner could go bundle up the next group of transactions and make a block out of it, right? But each block contains different amount of information. Like the nonce, how we talked about the number that's changed to figure out the target value, the different transactions. But how blocks are actually linked is that each block contains the previous block's hash value. So each block has its own hash value and the previous blocks. So that's how they're linked. It's saying like, oh, I'm this block. The next block should have my hash value. That's how I know that's the next block in the ordering.
Could you elaborate on how that, like, how one block having the previous block's hash value actually links them? I know that can you further expand on that?
It's this idea of pointers, I guess. It's
okay.
This will be a lot more technical than it actually is.
Maybe
so just the way you understand, it's like it's like a label. It's like, hey, you're deciding how you're gonna label them. Like, hey, we're gonna label this 0, and so if we're doing by numerical, we'll go 0, and the next one should be 1. The next one should be 2. The next one should be 3.
Right.
So what happens is you have block 0. Block 0, you calculate the hash value of block 0, right? And then that hash value, you say, all right, well, so the next block has to have that. So in order for a block to be created, they have to wait for that block to be finished, right? Because you can't get the hash value of the previous block if the block has not been created yet.
So when I'm creating my the hash block, my hash value for my current block, the hash value created from the previous block actually goes into SHA-256 or whatever hash function, right? And so if that's any different, then that would change my hash value, right? So like, does that make sense? Basically, like, the hash value from the previous block is used as part of the input for the hash value of the current block.
Yes.
And if it's because of that fact, like, you have to wait until you get the hash value from the previous block. And if it's any different than you guessed, or then that would create a different hash value, and that could be more or less than your target number.
Yes.
That's changing your lottery, and you can't do it until you know the hash value from the previous block.
Yes.
Okay.
Exactly.
I hope I explained that well. It's kind of confusing myself a little bit, but
it's a bit. And again, so knowing that, like, hey, I know that the block that follows me should have my hash value, and the hash value of that block is only calculated correctly only by having the previous block's hash value, right? And so that means, of course, they have to wait until that block is created.
Right.
And this is a super important idea because it gives the blockchain the attribute of being immutable. And so immutability. And if anybody doesn't know what mutability means, it just simply means that you cannot change what is written or recorded on that block or whatever. And so the way you think about it is, like, let's say a rogue hacker attempts to
rogue
just typing away, right? So the rogue hacker attempts to republish block 990, right? And so they have two options how they can do it. They can publish block 990 with new data and use an old hash value, right? So they like reinsert different transactions into that block, but they use the hash value they use the correct hash value of the previous, right? Or they use the hash value of the actual block, meaning that they use the correct hash value of the previous block.
Okay.
So making sense, if you think about it, block in there, they insert new transactions. They have the same hash value that is tying it to the previous. And then they have and then they keep the same old hash value as if they never changed the data in there,
Okay.
right? And then number 2 is that they new data, but then they use a new valid hash, right? So meaning
Right.
that they actually use the previous hash. They use I think actually, yeah, no. So they use like a
You're
different
explaining right,
hash
yeah.
value. They use like a different hash value for both of them. Like it's a different hash value of that's where it's
Doesn't
the
have to be the
previous.
same hash value from the previous one?
No, because what they can change it. They can change. I'll explain why.
Okay.
That's why it becomes invalid. But so they have the two options. So use a new data and then use new. They create a new valid hash value, right? And so for the first case where they're using the old hash value, that would like all the bookkeepers will know that's like invalid because it doesn't match the data inside. So like that old hash value was calculated based on old transactions, and therefore the new transactions does not create that hash value, right, from the old.
Okay, let me reiterate just for clarification.
Yeah.
So let's say that I didn't like block 990 because I spent a lot of money on block 990, so I want to change it. So I go into 990 and I change my transaction to being like I just fill it with a different transaction, so it's effectively not there. Then I use the hash value from what is it 989 that I need to create the valid block, but then I get a different hash value from the first 990. Like my 990 hash value is different from the first 990 hash value, and because they're different, that creates and that's used for the next block 991. I'd have to like that makes it invalid. Is that right? Okay.
Yeah.
And then I guess this kind of goes into like because like to keep my 990 block like to make sure everyone believe that it's true, I'd have to create a different chain of. Isn't that how that works? Do you want to expand on that?
Yeah, I'll explain on that in the next.
Okay.
That's coming up. But yeah, so the idea is that there's two ways they can publish it. 990, so they can publish the new block, new data, old hash value, right? An old hash value of what the old transaction were. Right.
Yeah.
So what the original hash value for block 990 was, or you were right on the idea that they still both of these cases are still using the previous hash value in it. But or the second one is that they use new data, but they recalculate the hash value based on the new data. So in the first case where they have the old hash value, that's automatically going to be wrong because it doesn't match what the data and the hash value does not match,
I see what
right?
you're saying.
And then for the second case, it doesn't 991 will not be correctly linked because there's going to be a new hash value,
right?
And it's going to say, hey, 991's like this block is not the block that I was referring to. This is the hash
block.
values don't match, so therefore it's invalid. And this is important because it gives you the mutability where it's not actually immutable because yeah, you could change it, but it makes it really, really hard, really, really difficult for you to change what's in those blocks.
Just real quick, how would you change it? Like if it was possible, like that, like how would you change it? Just to give everyone an idea of how hard it is.
So this idea goes with like the double spend, double spend problem, which is one of the last problems. So we'll touch on it right now. And so the double spend is like we mentioned, you spend the same coin twice. And so in order for someone to change a block, so you would have to change that block, right? So let's say again, block 990, you go, okay, I'm going to change the data in here, create a new hash value, right? And so remember the reason why this new hash value doesn't work in the blockchain is because the next one linking it, right, is like, oh, that doesn't refer to me, right?
Right.
So that means you have to create that block, then create every single block following that transaction. Every single
block.
And so, but at the same time that's happening, that you're trying to create every single block, there are also new blocks every 10 minutes being added to that chain.
So you have to keep up with everyone else, right?
So not only do you have to backtrack and create all the previous ones, you have to do that much faster than everybody else. Then you have to, on top of that, be able to beat all the other computers, the 10,000 other computers in the network that are creating and adding these blocks to the chain, making it super, super difficult. And again, like you are trying 2 to the power of 256 different probabilities when it comes to that nonce number, and it's insanely difficult.
If I recruited 5,000 people, could I do it?
Again,
or 10,000 to match it?
Again, this isn't based on the number of nodes you have in the network. This is based on how powerful.
If I was able to somehow summon enough money to buy enough computational power, is it possible?
No.
Why?
You would need to have 51% of the computing power. meaning you would have to have more power than half of every single computer, which if you have that much power, it would be
Yeah,
more.
I think we have more issues than Bitcoin.
Not even that. If you even had that much power that you've combined, it would be
hmm
it would just make more sense for you to just mine more Bitcoin, because that means you would
That's
beat
true.
every single person at getting the hash value. So why would you corrupt the protocol, therefore making the protocol lose its value? It will literally go to zero if someone
It's
broke the
true.
protocol. Therefore, then you're mining a coin that is useless. The incentive models for Bitcoin are like absolutely
Flawless.
incredible.
So we kind of jumped from 8 to 10, and just on what we have here. Do you want to go back and go over how we did you? And you touched on it, the longest chain.
Yeah, so this is an important idea, is that whenever there is a possibility that two blocks can be created at the same time. And
hmm
so what happens is that, so the block that gets created, those two blocks that's created, again, these blocks have to get propagated through the network. And so different miners will get them at different times. So they'll pick the one they hear first, they get first, and they'll work on that. They'll work on creating the next block for that chain, right? They'll take that, oh, that has value, add it to the new block, and then try to create, right? And so what the protocol is going to do is, while these different miners are working on the different chains at this point, now we have a divergence in our chain. They're going to pick the longest chain whenever, so like they keep creating them. If they keep creating at the same time, they're going to wait until there's one block, one chain that is the longest, and they're going to go, that is the longest proof of work, because again, the consensus is based on how long you're putting in work. So they're always going to go with the longest chain on that idea.
That makes sense.
Very straightforward, simple, but that is
That is how we construct or destruct, or however you want to say it, makes sense of a decentralized network or bookkeeping system in our economy, and which we know as Bitcoin. Do you have any thoughts on final thoughts? I guess
final thoughts.
I'm not gonna do a
All I'm
recap
going to say
because
is
it's
that
too much.
it is beautifully engineered. The incentive models are amazing, because every actor in the network has the incentive to keep the network afloat, keep it honest. And again, miners, anybody that is trying to hack it would have a much higher chance, much greater reward by playing fair than they would by trying to cheat it. Because again,
Right.
what is the point of you trying to hack and break it? Because you're just going to kill the integrity of the network, lose its value, and everything like that.
One thing I did say, I did realize just now, which we'll probably talk about more in different next episode,
Mhm.
is just that the only way that a hacker would hack Bitcoin is if its chief or their chief goal was to destroy Bitcoin, which
Yeah.
would really just be because if you have like if you have higher, I guess assets and other currencies that you
Mhm.
want to, like the dollar, and you
Yeah.
don't want Bitcoin to take over, or if you're a government that doesn't want, I don't know, just throwing thoughts out there. But it
With
is
all
now
that being
time
said,
for my favorite part of the episode, as always. Wait, did you have anything you want to say before? No. A quote or quotes from Armelicus Melius.
and with 2% left on my computer, we're going to blaze through this. A designer knows he has achieved perfection when there's nothing left to take away. Michael Saylor, Bitcoin's Jesus. And again, Bitcoin is a beautifully engineered solution to money. Money is a technology. Let's not forget that. If you understand money is a technology, you understand that Bitcoin is a superior money, because we're always going to want to use the best technology. And with all that being said, we do got to go. Thank you guys so much for listening. I am going to break down why Bitcoin is the best money in the next episode. So stick around. Stay tuned for next week. Make sure you like, subscribe, everything. Check out the blog, because Ben is dropping one on this. So I know it's really confusing information, but he's going to synthesize it in a great way. And until next time, peace.